Welcome to the 21st lecture for Physics 4B. We are wrapping up and reviewing magnetostatics in this lecture. In lieu of a more comprehensive topics review for magnetostatics, we have an excerpt from an old finals review of the portion covering concepts and approaches important in magnetostatics problem solving. Then, as examples, we have a couple homework questions in which the two main methods of deriving magnetic fields were demonstrated. And finally, we have a couple exam type questions that combine calculation of magnetic fields with working with the magnetic forces due to these fields. The questions are titled Solenoid and Charged Particle and Uniform Magnetic Fields. This is it for magnetostatics. In the next couple lectures, you will see the beginning of the unification of electricity and magnetism, and then we will spend some time looking at circuits. And I thought I would just start out with a very quick list of topics. Not the full list. I'm just going to try to fit my list on this corner here so that I don't have to erase it. So let me just give you the biggest breakdown, the big breakdown of the final exam topics that you should be reviewing. So these are the big topic breakdown of what may be covered on the final exam. Electrostatics, magnetism, and I guess there's one category that I call so that's the sort of the big category. And within each of these categories, there are some big chunks that I can mention that's worth mentioning. So in both dealing with electricity and magnetism, you are going to deal with some level of force. So you are going to deal with calculating forces and some level of kinematics that might come into as a result of dealing with these forces. I guess, so in electrostatics, that force is more or less trivial. It's, once you have electric field, so once you have electric field, then calculating electric force is trivial. You multiply by charge. And the kind of motion that results from the forces is also kind of simple in electrostatics. It ends up being something like a uniform acceleration, or it ends up being something like you would use conservation of energy to work out. Where it gets more interesting is actually with the magnetism. This is where you might actually have to review some kinematics. And you might have missed the question on exam 3 for that reason. It's because of the complicated form of magnetic force. So magnetic force is something that you should make sure you understood it, or if you didn't for some reason, review it. And because of the features of magnetic force, it most naturally results in something that looks like a circular motion. Because, magnetic force, I guess I can write it down here. Electromagnetic force is charge times electric field, which is trivial, not all that interesting, plus V cross B. And this cross product results in a very interesting features for the force. The force is always perpendicular to magnetic field. All right, doesn't really mean much. But it's also always perpendicular to velocity. And that results in the force naturally becoming a centripetal force. Because when a particle is moving in one direction, magnetic force always acts perpendicular to it. So it always changes the direction of the trajectory, but doesn't ever speed it up or slow it down. So whenever you have magnetic field and a charged particle moving, it sort of naturally results in a circular motion. So let me call it magnetic force and circular motion. So this is where you might have to review some kinematics, because there are some formulas and concepts related to the circular motion that you could have forgotten since physics 4a. So, all right, so that's a little bit of piece that might tie back to physics 4a and what the sort of mechanics you're supposed to know. The rest is more, well, I'll just go through it. Let me go through the rest of the electromagnetism topics. So in electrostatics, there's an electric field. So there is how to calculate electric field. And you calculate the electric field either using Coulomb's law. That's when you're either mostly dealing with the point charges, or you're dealing with a charge distribution that doesn't have quite enough symmetry. If we are in one of the three symmetric geometric situation, then you would use Gauss's law to find the electric field. And I have to tell you that the topic that really a lot of people need to review is application of Gauss's law. It's Coulomb's law. It's a kind of tedious calculation. I can't believe that there are people here who don't know how to apply Coulomb's law to do the integral and all this stuff. So I don't mean to say that's easy. But this is what I mean. A lot of people really need to review Gauss's law. Is that Gauss's law, once you know how to use it, it can be really simple. It can be easy. But to too many of you here, because you didn't study, you never understood the argument, it's not easy for you. And this is something where you spend 30 minutes to an hour, focus the study, focusing on actually understanding what you are reading, you can actually get it. It's the application of Coulomb's law, where you have to set up the integral and do the integral, it can be super complicated. But Gauss's law application, that's something that ought to be simple. I mean, I don't mean it's easy. It's mathematically sophisticated. It does involve mathematically advanced argument. But once you get it, then it's really an easy calculation to do. So that's why I'm highlighting this as something that people should review. If you didn't learn this when you are studying for exam 2, now learn it as you are studying for final exam. You will see it on final exam. The last set of sort of big topic we cover in electrostatics. So we dealt with the forces. The other physically important quantity is energy. So what we introduce is the things that deal with the energy, voltage. So this is the other big topic we covered in connection with the electrostatics. And because I'm limiting myself to this tiny space, I'm not able to list a bunch of other stuff, like things dealing with the conductors, things dealing with some particular special situations, all this stuff. Well, it should come up as you are studying electrostatics, like interaction, electric field due to a dipole or things like that. But I'm just, if I had to mention 2 words with electrostatics, it would be fields and voltage. And everything else that we do somehow ties to one or the other. Good? Okay, let's move on to magnetism. So with the magnetism, it's also the same thing. The very first thing that I would mention is magnetic field. So like with electricity, where to calculate the electric field, we had Coulomb's law and Gauss's law. They're kind of equivalent to each other. The difference is that one is more convenient in a limited set of situations. And if that fails, if this convenient method fails, then you have to move on to brute force method. So with magnetism, magnetic field, it's the same thing. You have 2 methods. The brute force method that'll work all the time, except it's calculationally complicated. That's the Biot-Savart's law. And actually, I think a lot of people were doing this on the exam 3. you are using Biot-Savart's law to calculate the magnetic field of due to a loop of current. That is a typical example of application of Biot-Savart's law. That's a situation where you see a magnetic field, but a loop of current does not have enough symmetry to use the next thing. So a lot of people are doing that on the exam. I guess the only reason I say this like that's not the thing you should have done is that that question actually gave you the magnetic field. So you didn't have to waste your time recalculating something that was given in the problem. But I might give you a problem where I'm asking you to calculate this, and I'm not giving you the answer. You have to do it yourself. So it's good that you know how to do it. You know how to use Biot-Savart's law for certain situations. And because it involves integral, in this class you are not going to be tested on a really wide variety of geometries. I can't, because you have limited amount of time during the exam. So like with electricity, the other important thing is Ampere's law. And I say the same thing for Ampere's law that I just said for Gauss's law, that people could really stand to review application of Ampere's law. Because once again, like with Gauss's law, it's not hard. It involves sophisticated argument and reasoning, and it is advanced. It's not something that I would feel comfortable teaching in high school or middle school, unlike some of the things that we teach here. Understanding Ampere's law does involve college level, does involve, it's actually difficult to cover Ampere's law in algebra-based physics. It does involve a level of mathematical sophistication that only someone who was able to successfully pass calculus can understand. But once you understand that underlying concept and the argument, the actual calculation is super simple. And there's really no excuse for anyone here not to know how to apply Ampere's law. And I guess on the exam, sometimes I see this where people just write down set of, so this is, I guess, what I can say is what I see on exam 3 that people were doing wrong. So it's essentially a version of the correct answer, except you are missing some key things. As in, so this was one of the example of where you had to use Ampere's law, right? So the kind of an wrong answer I would see, you'd have all these mathematical expressions. You'd have this, 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 and this. And that's the only thing you would have. This is what I see as an indication of someone who actually did not understand the argument. And the only thing you did is you copied down these equations into your formula sheet, and you are just copying them from your formula card onto this. You do not get full credit for that answer. The most I would ever give for an answer like that is 3 out of 5. If you're planning for that, then great. You're not planning to get an A or B. You're not, you just want to pass, and I'm okay with that actually. If you just want to pass, and that's the level of effort you are willing to put in, then do. I cannot change your goal for you. But if you are trying to actually do well, you need everything else that's here. The one key part that you really need to have, and this is the indication that you didn't understand the thing when you wrote down all the correct equations. If you don't have Amperian loop, that's an indication that whatever you wrote down, you actually didn't understand. Because there's no way you could write down any of this without actually having a loop in mind. And if you had a loop in mind, you better write it down so that I know what's it. I can't read your mind. I can only grade what's written on the thing. So at a minimum, when you are applying Ampere's law, you have to have the Amperian loop drawn, because you cannot apply Ampere's law without it. And really what I'm hoping for is that people would even write down these. I keep drawing analogies to English class here. It's because people come in with this mistaken understanding that all that physics is math. It's not. There are a lot of good mathematicians who are terrible physicists because they don't understand the physical concepts that go into physics. And a good chunk of physics does have to involve using the English language or whatever language, but this is class. I only understand English. So you have to use some language to explain what you are doing. So ideally, you should be able to explain your line of reasoning in some language other than mathematical equations. So this is what I mean when I say you should review Ampere's law. Both for Ampere's law and Gauss's law, your best resource will be portable TA. The portable TA has some examples of application of Gauss's law and application of Ampere's law. And those problems are some of the longest answers that the author writes. It's because the proper explanation of steps actually does require a lot of words to explain. And what I'm telling you have to do if you are trying to do well, that you actually have to understand that argument so that you can reproduce some of it on the exam. So Ampere's law is the big one of the big thing in magnetism that everyone here should know. It's I guess by itself Gauss's law and Ampere's law, it doesn't look like there's a lot of application. It doesn't need to tie back into the forces for it to be useful in whatever you might be doing in research or engineering. Let's see, I thought there was one more thing I should bring up with the magnetism. Like it's a big piece that I cannot not bring up. You have the magnetic field. I feel like I missed something. It might be that with the magnetism, the big thing is the force. That magnetic force is pretty complicated, so the particle path would look complicated. Let me make sure I didn't miss something, because I'm pretty sure I didn't miss anything in the exam study guide. So let me look back at exam 3 study guide. Let's see, magnetism, magnetic field calculation. I guess that's it. So the biggest thing, the other big thing would be something that I already mentioned, the magnetic force. And with the electricity, I don't really bring a lot of attention to the electric force, and that's because I think it's kind of trivial. There's nothing interesting dealing with the electric force. It's more or less what you would have expected intuitively. But magnetic force is not. The kind of motion that results in the kind of the path of the particles, that's something that actually requires a level of mathematical understanding to work out. One example of that was actually on exam 3, which, so this is one question where I would say it's not entirely your fault that you're not getting it. I tried this question, I guess 2 semesters so far, and very few people get it. And I'm hoping in a future semester to teach this class in a way where some people get it. So it's this question, part D, about magnetic bottle. And the first time I gave this question, I mistakenly thought this example was in Giancoli. It's not. It's not an example in Giancoli, so you could have been studying a lot, reading through the textbook, and still never have seen it. You had to have the correct textbook that's not here. Let me get it. It's probably in my office. Okay, so I remember that example from the textbook that I studied my lower division physics out of. So that's why I thought, oh, that's a good standard example. Should be in Giancoli. It's not. It's in this textbook. So if you are reading the correct textbook, then you would have seen it. But you can still. So all this means is that if you haven't seen the example before, then it's harder to get it on an exam. But I guess the ideal goal I have is that you understand the magnetism well enough, you understand the magnetic force well enough that you can actually reason through it. That's where I was trying to give you some hint here. Assume that the initial velocity is mostly perpendicular, but there's a small component that's parallel. So if this is the part that I drew in the solution. So this is maybe the initial velocity. And a lot of you got the fact that the force due to magnetic field will be perpendicular and it'll result in going in circle. The part that I'm hoping some people will get at some point. So because this says component of velocity that's parallel, this will actually go in some kind of a helical path. The helical path that some people got in the previous question here. That if you have a particle that's moving at some angle, then it follows a path that looks like this, a helix. Right? So as it follows that helical path, this will start to drift away in this direction. So the analysis you had to go through was something like this. What's the force on the particle as it's around this portion here, as it's about to drift out of the bottle? Then when you look at the force carefully, so this is the direction of magnetic field, force on the particle when it's here, you'd realize that the V cross B has a component that's pushing the particle backward, back towards the center of the arrangement. And I try this question every once so often, and people don't get it, mainly because I think we need to have done more emphasis on the sort of result of the magnetic force. And but that's more of a reminder for me in the future semester. But what doesn't change, what I'll still hold you to for this semester still. So I probably won't give this magnetic bottle question on the final. I won't do that. But what you should know is how to work out the magnetic force for a particular case that's in the problem. That using the right-hand rule and cross product, and work out the consequence. What would be the particle path following that? I guess, let me leave it there. You have enough homework questions. So is nothing that I would ask you on the final exam that's more difficult than what's already in your homework question for motion of a particle under magnetic force. Okay, so this is so these are the two big groupings of topics where it's just electricity alone, no magnetism, and this is sort of like magnetism alone, no electricity. There's no electric field anywhere here that we are bringing. There's a current because that's where magnetic field comes from, but that's where we limit ourselves to. So yeah, and so there are different ways you can do this question. You could try to do it by looking at formulas from the textbook and maybe kind of modify them a little bit intuitively. I guess you could do it that way. Let me try to do this in the proper way by actually doing the integral. So this is what the question is asking for. What is the magnetic field at point P due to the current I flowing in the wire as shown? Give your answer in terms of given variables and physical. So A is the inner radius, B is the outer radius, and numerical constant. Yeah. I think the direction is the easier piece to answer. So this is a good practice of right-hand rule. So there's a shortcut right-hand rule you can use to get to it. So where I guess you would be using the shortcut right-hand rule, recognizing this as a half of a loop, and this is another half of a loop. You can do that. Let me do the version without any shortcuts here. So one without any shortcuts is one where you are basically doing the cross product in Biot-Savart's law. So Biot-Savart's law says that small contribution to magnetic field is equal to, there's a numerical coefficient here, and then current times dl, small segment of the wire, cross product with r hat, that gives you the direction, and the other coefficient divided by r squared. It's an inverse square law, and the coefficient here is Coulomb constant divided by c squared. Or if you want, you could write this as mu naught over 4 pi. Both are fine. I'm trying to retain use of Coulomb constant this semester. So you can just do this cross product here. The direction of current cross product with the r hat. So if I imagine taking, for example, this segment here. So in this segment, my direction of dl goes this way in the direction of current. And r hat always points from the source to the point where you are calculating the field. So this is the direction of r hat. So you just do the cross product. dl cross, dl, yeah. And then, towards the circle. So this is the orientation of my hand that will allow me to bend my fingers in the direction of r hat.
So the cross product, my thumb is pointing out of the screen towards you. So that's the direction of the cross product. So this inner half loop contributes magnetic field pointing out of the screen towards you. Now, when you look at the outer loop, it goes the other way because your direction of DL now goes clockwise, and our head is still pointing inward. So when you our head is still pointing inward. So when you do, okay, my hand points to right-ish, and then this is how my hand is oriented so that I can bend my finger towards the center of the circle, then my thumb points into the screen. So you have these two competing contributions from the magnetic field from the inner loop of radius A and magnetic field from the outer loop of radius B. And this is where some sense of intuition is useful. Intuition that comes from the fact that magnetism is an inverse square law. So the farther away something is, all things being same, the influence will be weaker. So as these two competing magnetic fields add, the term that will win out is the one that's coming from the inner radius, inner loop. So magnetic field overall will point out of page. Oh, and just so that it doesn't look like I forgot about these two segments, these two segments are interesting in that they contribute no magnetic field at this point. Watch. So at this point, this is the direction of DL, and the direction of our head points this way. They are anti-parallel. So when you do DL cross R, the angle here is 180 degrees. Sine of 180 degrees is 0. So this contributes to no magnetic field at this point. And same thing with this segment here. DL points towards the center, and that's the same direction as our head. So cross product of these two vectors will give you just 0. So as you're doing this calculation, the only thing you have to worry about are the two semicircular loops. Those are the only current distributions that will contribute to magnetic field in the center. I mean, these do create magnetic field, but just not at the center point. So, okay, the second part of the question, field point and has magnitude. So this is where you have to just go through the calculation. We have Biot-Savart's law. So for the total magnetic field, due to the total magnetic field at P, due to the entire current distribution, is going to be an integral. I'll integrate along the path DL. And that integral will, let me set it up. It looks like this. So let me start out with just the first symbolic expression. This is integral around the entire current loop. The coefficient times the I is going to be a constant. It doesn't change. Times DL cross R head is something I'll have to work out. And same deal with the R squared. Now, as you look at this schematic expression, that's a reminder of more of a reminder of what to do than actual thing you can calculate with. I hope you see this simplification you will get. For the integral along the inner loop, the distance r remains constant. It remains at a. So if I could do the integral for this portion separately from the integral over this portion, it'll give me some expression that's relatively easy to deal with. So I'm going to do exactly that. I'm going to split up this integral that I'm doing along DL into one portion, that's the inner loop, and then the other portion, the outer loop. And as I mentioned, along this portion, there's no contribution to magnetic field, so I can skip those. So I'm going to be integrating around the loop of radius a. Same coefficients, k over c squared, and I can plug in some values as I do this now. I times dl cross r hat. And here, instead of r squared, I know the distance, that's a, for all the points along this path, starting from here. So I can just say divided by a squared. And let me finish writing the second portion of the contribution, plus the integral around the loop of radius b, k over c squared I dl cross r hat divided by, and here the radius for this loop is b, so I can say b squared. Now I can do some simplifications in situ, in place. So for each one of these points, I hope you see that dl and r hat are always perpendicular. It's kind of the nice thing about this particular geometry, that that we are dealing with the current that's tangent to the circle, and the radial direction is always perpendicular to the tangent direction. So in terms of the magnitude of dl and r hat, dl cross r hat, it's always going to be dl times r hat, because it's just always perpendicular, or perpendicular along the entire path. Now, that's the magnitude. And in terms of the directions, that's exactly what we worked out here. So we could say, okay, out of page is positive, then this integral will give me a positive value, and if I modify the second term so that, okay, I'm going to be subtracting what I get from my second integral, then I can work out the integral here, just worrying about the magnitudes. The directions have already all been accounted for. And here it's nice because dl cross r hat is always it's perpendicular to the screen. So I can describe that as either as being positive or negative. So with those in mind, this dl cross r hat, if we agree that these expressions are going to be the scalar indicating the magnitude, then dl cross r hat is just dl, because it's that's the only quantity there that that's not a unit vector. R hat is a unit vector that's length 1. And same thing with the second expression. So this dl cross r hat, it's just dl, the length integral. And this is the final piece here. As you look at this integrand, I hope you see that nothing here depends on the everything here is constant. These are constant, current is constant, distance is constant. So what this really is, this integral, it really just applies to this dl around the loop. So it's this integral over this half a circle loop of dl, and so I don't actually have to do this integral explicitly without doing, I just know this is 1/2 of a circumference. So it is which is equal to pi times a. So we get situations like this often when we do magnetism and electricity. We set up the integral, we are all ready to do the integral, and then suddenly, we don't need to. Now this is more common as we apply Gauss's law and Ampere's law, where we pretend to do all this integral with no intention of actually doing the integral. Here, I had every intention to do the integral, and there are situations where you will actually have to do the integral, especially when applying Biot-Savart's law. But in this particular case, I don't need to. So the first term will simply become k over c squared times, so pi a, one factor of will cancel one factor of a, so this will be I times pi over a minus the second, so when I do this integral over dl, it's gonna give me pi times b. So it'll be ke over c squared times I pi, and one factor of b will cancel one factor of b squared from denominator, so I pi over b. So this is it. I can simplify it a little bit. I can factor some things. In fact, let me plug this into the question and just factor it in situ. So magnetic field point out of page, and here I would just say, okay, I'm gonna factor out pi ke times I over c squared. So do I have, okay, pi times ke times I divided by c squared. And then after factoring those out, I have 1 over a minus 1 over b. So that's it. I hope. Yeah. Yeah. So as it turns out, at the very end, the calculation isn't too complicated. But this setting up this, it's challenging. Unless you've seen it done, or unless you've had some time to think it through, I can imagine this part tripping up people, which is why I wanted to do this question. Okay, so this is the question. It says the accompanying figure shows a cross section of a long, hollow, cylindrical conductor of some inner radius and outer radius. So I hope as you read the description and look at the figure that you have this image in mind. Let me show it. I happen to have these. If I had extra time, I would do this demo. So what they're describing is basically something that looks like a pipe. So here's an example of a copper tube, and what the cross section there is showing is a copper tube like this. It's showing you this view. So so with that in mind, what they're saying is there's a 45, there's some amount of current. Let me just label this I naught, distributed uniformly over the cross section, flows into the page. So I have current that are flowing into the page. I think I want to define a new quantity, or quantity that you have seen in textbook, which is the current density. So let me label those so that I don't confuse myself. So R1 is 4 centimeters, and R2 is 6 centimeters. And all these are, so these distances are generated so that it'll always give you the distances this way. The first distance will be smaller than R1. The second distance will be between R1 and R2. And the third distance will be greater than R3, or not R3, greater than R2. That's how it'll always be. And so the answer to A and C is fairly simple. So let me do this question properly once for B, and that'll be a good starting place to get quick answers to A and C. So let me do it that way. So with that in mind, I think I need to define the current density. This is a quantity that you have seen in the textbook. Current density is defined so that it's the amount of current considered as a vector quantity divided by the area. That's the current density. Oh, I guess I don't actually have to make this a vector because I'm not going to use the vector sense. I do have to mind if it's into the page or out of the page, but let me just leave that here. So I have the current given. So I need to figure this portion out. So it's the area of this, what is it called? The annulus. I think that's the 2D geometry. The area of that, the ring is, it's the area of the outer circle minus the area of the inner circle.
So A should be pi r2 squared minus pi r1 squared. Or if you want to simplify it a little bit, pi times r2 squared minus r1 squared. So that's going to be the expression for the current density J. Let me write it here for now. And I'm going to be using the letter J for most of this question. In fact, all of the question, knowing that with the given numbers, you can plug numbers in here to get the current density in the units of, I don't know, area per square centimeter. So for the rest of the question, I'll use the symbol J because that'll make things a little bit simpler. So let me do B first, since B is the most challenging setup. Once I do B, then the rest is a little bit easier. So maybe not so much. Let me start out with a B. So this is an application of Ampere's law question. You are given the current, and the law that you want to use, it has this form. The line integral of B dot dl is given by, let me use the coefficient that I prefer, 4 pi times Coulomb constant divided by c squared times the current enclosed. And there are two things that you need to consider in applying this. The first part is this part here, that magnetic field is inside the integral. So you need some clever argument to be able to get the magnetic field out of the integral. And that clever argument is the symmetry argument. You have to think of a symmetry that fits with this setup, and you have to choose your loop dl that you are integrating over in such a way that the dot product of the magnetic field and dl will be constant, or it'll be something that you can work out without knowing the exact value of b over the path. So for a cylindrical arrangement like this, it has really, it has two symmetries that are useful. One is a translational symmetry, as in if you are looking at it from side, as you translate that cylinder, either way, nothing's real. So, this is not infinite, so you see something changing. But if this were infinitely long, then as I move it, nothing will really be changing. So you have the translational symmetry that, and what the translational symmetry gives you is that you can just pick one cross section, like this one, work things out for that one cross section, and everything will be fine. You don't have to consider another cross section. And it also gives you the rough direction of the magnetic field. With that translational symmetry, the only direction your magnetic fields can be in that's consistent with the Biot-Savart law and everything is, let me kind of get the direction right. So current going into the screen, and so the magnetic field should be clockwise. So the only possible directions of magnetic field is kind of circular going this way. If we didn't have the translational symmetry, then there might be a component of magnetic field that's perpendicular to the screen, but you don't have that. That's not consistent with the translational symmetry and the reflection symmetry. And so that's one symmetry that kind of constrains what direction magnetic field can be. And the other symmetry that will be useful is the rotational symmetry. So, rotational symmetry, like rotation this way. So as you imagine rotating this cylinder, maybe in this way, you are not really changing anything, which means magnetic field at this point should be the same magnetic field at this point, as long as the distance is the same. So the geometry for the Amperian loop that will exploit all these existing symmetries is a circle. It's a circle going this way. So when I have an Amperian loop that's chosen specifically to exploit this symmetry, a circle that's concentric with these cross-sectional things, then the magnetic field at all the points will be the same. So with that argument, you can pull the magnetic field out of the integral, and you can justify writing down this expression, that this is equal to magnetic field times the line integral of dl. And I just can overemphasize how important this justification step is, because this is kind of like magic in the sense that you have to say the right words. And when you don't say the right words, nothing happens. When you say the right words, you have done this magic proof. So, okay, I've done that step and applied the symmetry, made the symmetry argument, and pulled the magnetic field out of the integral. Then this integral here is actually really simple. It's a line integral of dl around the circle, so that's just the circumference of the circle. So I've been pretending that I'm going to do this integral. I don't end up doing it. I can just write down the left-hand side as b times 2 pi r. Good. Now the right-hand side needs a little bit of work for part B, which is why we are doing that first. So let me write down the parts that need work. It's the part about the current enclosed. So, so this loop here, it only encloses the current in the region that I'm shading. So as you can see, it doesn't enclose all the current. It only encloses the current in this portion. So, so I need to figure out how much current is in this portion. And I feel most comfortable doing that more geometrically than other more complicated things I could do, because this is the place where you could get too formalistic. You could say I enclosed, that's the surface integral of JDA, current density times the area element. So you integrate over the annulus thing, and that'll give you current enclosed. But I think that's kind of more formalistic method than something that I need. I can kind of stare at this for a while and figure, all right, so I have this as the area of the cross section, and I can write down an expression for the area that's enclosed within this radius r. So area that's enclosed within the radius r, it's gonna be, so the r will become my outer circle, pi r squared, minus, I still have to subtract off this inner circle, r1 squared. And I think intuitively what I would say the current enclosed is, well, take the ratio of the total current flowing divided by the area of the cross section, or that's my current density, times the area of the portion of the cross section that I'm enclosing. So that is going to be my I enclosed. So let me write that down. Then for the right hand side, what I get is 4 pi Coulomb constant over c squared times, let me write out I naught over a times AR. And let me do a little bit of the remaining algebra. Solving for b here, you get b is equal to 4 pi ke over c squared times I naught over a times 2 pi r times AR. And this is the place where you could just plug in the numbers. You have enough numbers to just plug in the numbers and finish it out that way. Or you could work this out analytically. And I'll say for this question, I don't have a preference either way. There is something you can get out of by writing out the analytical expression. So let me do that. Let me show you what cancels and why it might be
semi-useful. Pi r2 squared minus r1 squared times 2 pi r, and AR is pi r squared minus r1 squared. And the part that is could be kind of useful is if you separate out this term, you see that for the first term, that this r can cancel one factor of r. So there's one term that goes linearly with the radius. So the magnetic field as a function of r, there's a term that goes as linear. That's a kind of a feature you begin to see when you have a uniform things, uniform charge density, uniform current density, and noticing that is worth something. But the thing that's complicating here is that you have this term here too. So you don't quite get that simple things. That's why I'm a bit ambivalent towards should you just plug in the numbers or do the algebra? Do whichever. Either way, the answer you're plugging in here is a numerical answer anyway. Let me finish up the part A and B. Part A is simple. If your loop is inside the innermost, inside the inner radius of the conductor, then you are enclosing zero current. So you would get zero zero as your magnetic field after you've made this symmetry argument. You do have to make the symmetry argument. It's not correct that whenever you enclose a zero current, magnetic field is necessarily zero. That's not the case. The only thing that's guaranteed is that this integral is zero. And for this setup, you can make the symmetry argument to pull out the magnetic field. And from here, the right-hand side being zero means magnetic field is zero. So that's simple enough. For part C, you can, well, imagine a loop that's outside both of the conductors. Then you can actually go through the exact same calculation that we did earlier. The one care that you need to take is the different meanings that different radii r take. So this r here is associated with the radius of the path. So this is the r. So I let this be. That's the r that we had before. So I let this be. I'm not going to change that. But this r here, that's the r from here. And that's associated with the outer edge of the current distribution. And that stops at R2. So since that stops at R2, this R here, it actually becomes R2, not R. And once you have that, then I hope you see that these two actually cancel out. Oh, and pi's cancel out. And this pi cancels out, this two cancels out, and you are left with the expression that looks like, well, magnetic field due to an infinite line of current, 2ke over I naught over c squared times r. That's the same formula as the magnetic field due to an infinite line of current, and that's what you get for part C. And it kind of simplifies that way when you carefully replace the quantities that you had in the derivation for part B. So this is an Ampere's law application question. Make sure as you're going through this question and plugging in the answers that you understand the argument that goes into that. That's the kind of thing that that my goal is to get to in the timed assessment follow-up meeting, because the proof argument like that, it's you have to kind of poke at different places to make sure that you understood all the things that you are supposed to understand. And yeah, so let me leave that there. although theoretically I wrote these questions and I have written solutions for them at least once, when I gave them as midterm exam questions. But it's been a while and I didn't do any work to prepare for this session. So if I somehow mess up and am not able to answer correctly, I apologize. I'll try to redo it. But I'm hoping whatever question I get that I can actually answer it correctly. So we'll see. Let me start. I have 20 minutes from this point on. All right, it says consider an infinite solenoid. Okay. Make me feel better. And I like a application of Ampere's law question. Those are easier. It's harder for me to forget those because it involves application of symmetry and all that. So let me actually copy this thing over so that I don't have to redraw the whole solenoid thing. Okay. Give your answers. Yeah. Using Ampere's law, show that the magnet to the magnetic field inside the solenoid is that. And I give you the answer so that if you simply give me the expression, like, okay, you get no credit for that. So let me start by stating the Ampere's law. Ampere's law says this. I'm going to state the version with the mu naught first because that's the version I have memorized. It says the line integral over a closed loop of B dot dl is equal to mu naught times current enclosed. And because there's that equivalence of mu naught is equal to 4 pi ke over c squared, in terms of the coefficients that I'm trying to use, it'll be 4 pi Coulomb constant over, there's speed of light here for some reason, times I enclosed. That's Ampere's law. So in applying Ampere's law to find the magnetic field, you first need to have a sense of the direction of magnetic field. With the solenoid, so let's see, I'm going to use the shortcut rule. So think of one of these loop of current. So on the right, coming out of, on the right, going into the page, and on the left, coming out of the page. Okay, and in that direction, the thumb is pointing downward, so the magnetic field within the loop should be pointed downward. Let me just double check that from my perspective. Yeah, okay, good. And if anything, if there's any magnetic field outside of the solenoid, it would be pointed upward. Although that's something you can actually prove that it's a zero. So from symmetry, there's a rotational symmetry and there's a translational symmetry. From symmetry, you can argue that the magnetic field within the solenoid is uniform. Or actually, not quite. I don't think you can argue that. What you can argue so far is that magnetic field along this line is constant. So if you are considering a different line, for example here, then your magnetic field actually might be different. Because there's no symmetry operation with rotation or translation that will take you from this point to that point. So that particular bit actually needs additional step. But I have this length of space where I think my magnetic field is constant, and that's good enough for me now. So let me consider this Amperian loop. The Amperian loop I'm considering, it'll go along the magnetic field here, so that I can accumulate B dot dl along this point, and then it's going to turn 90 degrees. So that along this segment, I accumulate no B dot dl. It's perpendicular 90 degrees. And then after going through here, I'm going to go all the way out to infinity. And only when I've reached the infinity, I'm going to turn around and start going up this way. And because it's out at infinity, I can kind of take a guess the magnetic field here has to be zero. I can think of the solenoid looking like an infinite line of current. From infinity away, it'll look zero-ish. So let me finish the thing here. So this is going to be my Amperian loop. So this is a very beautiful loop in that the only segment that's contributing anything to this line integral is this segment here. So I can write this down for A, that that the line integral of B dot dl is actually going to become a very simple integral. It's going to be so it's going to be integral of magnetic field B times the dl for this one segment. And I think I can actually write this rather simply. If I give a symbol for this height of the loop, let me call that lowercase h, then because I think a magnetic field will be uniform along that length, I can say this integral is simply going to be the magnetic field at that position times the height h. And we say this is equal to 4 pi Ke over c squared times current enclosed. And now I need an expression for current enclosed. I have this expression I naught for current per loop. And I believe I'm told n, the loop density. So actually I can, if I'm counting the number of loops, the number of loops would be the density times the height, h here. That's going to be number of loops. So that times, so I naught times nh will give me the enclosed current. So with that, I can write this equation out. Left hand side, B times h is equal to right hand side, 4 pi Ke over c squared times enclosed current, I naught nh, and I see this beautiful cancellation. The arbitrary parameter h cancels out. So I get the expression B is equal to 4 pi Ke c squared I naught n. And that is the same expression as what we have here, some ordering. So that's the correct answer. Now, if you stop here, you're only maybe 2/3 of the way right, not full way right. So what you have to finish up is this argument, that you have this expression for the magnetic field, and now you consider moving this segment, keeping this loop mostly intact, but moving it around a little bit. Maybe you want to move this, maybe you want to move this portion of the loop a little bit in. Now, here's the wonderful thing when you do. When you move it in, you have changed where you are integrating over, but you haven't changed anything else. Current is the same, symmetry consideration is the same, which means this formula that we derived for a different location, it continues to apply. That's true wherever you put this segment. So that is the proof that magnetic field inside the solenoid must be uniform, because it doesn't depend on where you put this. And as for magnetic field outside the solenoid being zero, you get that by moving this portion of the segment. When you move it, because along this length the contribution was zero, you can move this all the way in right up until here without changing anything. So which means so the line integral is the same, and that can only be true if the magnetic field immediately outside the solenoid is zero. So that's the last bit of argument you have to make to say, one, inside field is uniform at this strength, and immediately outside it's zero. So Ampere magnetic field inside the solenoid points downward. Amperian loop of a rectangular shape going along the magnetic field inside the solenoid, and the horizontal segment perpendicular to the B field was chosen for argument using Ampere's law. Symmetry considerations give line integral simplifying to B times h, where h is the... Okay, I have 10 minutes. Let me go more quickly. Okay, find the direction and magnitude of force on each loop due to solenoid wire 1. Oh, I see. So let me copy and paste this. I'll be a little bit more sparse with the explanations. So I think I might be running out of time. Uh, so in B, so let me start with this. So I have this magnetic field, and inside the field within the loop, B is what I derived, 4 pi k e over c squared and I naught. Now, immediately outside, where magnetic field could have been going the other way, magnetic field is actually zero. So there's this legitimate question of what is the magnetic field, effective magnetic field along this point, where there's an abrupt transition from this value to zero. And that's why it's giving this hint. If the magnetic field is very different, not smoothly different from the magnet on the other side, also the effective field is the average. So for the B effective, based on that hint, I'm gonna say B effective is this thing divided by 2. So 2 pi ke over c squared and I naught. That's what I'm gonna say is the magnetic field at all the points on the loop along the solenoid. The loop looking like this. So now let's figure out the force. So direction and magnitude of force on each loop. Okay. Why do I have to say per length? I don't think I have to say per length. Do I have? Yeah, I have a radius r. So I don't think I need to say per length. So really all I'm trying to do is let me draw the top-down view. I have a ring like this, and in the top-down view, so this current was coming out, so current was pointed this way. This is the direction of current, and the magnetic field was pointed downward. So when I view from top, it'll be going into the page, and it's everywhere. So I can do the magnetic force on a current carrying wire is the amount of current times the L as the vector cross with the B. So I can do IL cross B. So let me do it on this side. So the left hand side. So current is going up. Magnetic field is pointed into the screen. So doing IL cross B, I get a force that's pointing to left. And as I imagine going around and doing that, force will always be kind of pointed outward this way. So yeah, let me just do it from my perspective to be sure. So yeah. I think since the current and magnetic field is perpendicular, I think so I guess it's saying per length, because if I'm simply adding these all up, it's gonna be zero. Net force adds up to zero. But you can think about pressure, the kind of pressure pulling it out. Then that'll be FB of I times B. So this FB per length will be I times B. Yeah. So let's put it this way. So I'm gonna say FB per length is equal to current times B, since I is perpendicular to B. Figures in attached work. And the direction is pushing the loop outward, as if to make radius larger. All right, got 6 minutes. Okay, part C. Suppose that particle. Okay, can I just copy image? Oh wow, yeah, it worked. Okay, so I have that, and let's see. Enters the solenoid, somehow it passes, yeah, V0, okay. Describe the path of the particle after it enters the solenoid, assuming that. Okay, let's just start with the magnetic field direction that we already know. Already know that, and the Q is, yeah, positive, okay. So let's just start by working out V cross B. So V cross B. By the way, because both V and B are in the plane, the force will be perpendicular to the plane. You are really only choosing between is the force perpendicular going into the screen or is the force perpendicular coming out of the screen. That's all you are choosing. And when you do right hand rule, V cross B, the thumb is pointed out of the screen. So the choice that holds is just the one that's going out of the screen. Just do it from my perspective. So as the particle is coming in right now here, it's experiencing force that's pushing it out this way. So it'll start to bend outward this way. So it'll have like a circular component that I think it goes like this. Out of screen here. And then once it comes around and it's going this way, then it'll be going, the force will be going into the screen, V cross B into the screen. Yeah. So the actual path of the particle will look something like a helical thing, like this. That will be the actual path of the particle. So describe path, assuming describe path both qualitatively and quantitatively. Okay. So qualitatively, path will appear helical with the component of velocity along B remaining constant. So that would be like, this would be V not parallel, that's constant, and there will be component V not perpendicular. Along the B remain constant, and the speed for the component perpendicular B will be constant, but the direction will change in a way consistent with uniform circular motion in 2D. Up here, looking from above, the helical path above, meaning particle moving away from viewer, the helical path will appear. Let's see. So that this is coming out of the page into. So just imagining rotating this shape in your head. So looking at it from above, this will be this way, this will be that way, so it'll be counterclockwise. The helical appear counterclockwise. Quantitatively, the radius will be consistent with the cyclotron motion radius. We'll work it out later, where the V is the component of velocity perpendicular to the magnetic field. So that will be given by V naught sine theta. V naught sine theta. And I gave this question because I think as I work it out, the time might run out. So let's work out the cyclotron motion thing. So I have this radius r that I'm trying to work out, and this says the component of velocity in this view, that's V naught sine theta, and there's magnetic field perpendicular to it, kind of into the page, out of the page, into the page, this way. Yeah. So that V cross. Yeah. Okay, it all works. So this is what I have to write down. The magnetic force is gonna be Q, this component V naught sine theta times B, and this should be equal to the centripetal force, M V naught sine theta squared over R. I'm just ignoring the parallel component. I can do that. You can also do like shift of reference frame. So solving for R here is one factor of that cancels. It's mv naught sine theta over qb. That's R. Do I have time to type it in? Okay, yeah, I do. The cyclotron motion radius is R is equal to m times v naught sine theta divided by qb. Now, unfortunately, I won't have the solutions to display to you right now. Although I can do this. I can bring up the solution of the question that this came out of and show you that and compare that. I think I can do that. So let me let the time run out, and then I will attach my work, and then I will go dig up the solution and see if I made a mistake, or see if I made a mistake then or now. So let me go look up the past midterm exam that this question is out of. It'll take a little bit of time. Let me just do that on my second screen. This is the one. Okay. So let me bring this up. Yeah, kind of lucky. Could have taken longer. So this is the solution from then. It comes from an old midterm exam question that I call the solenoid and charged particle. And you consider finite infinite solenoid. This is the drawing, the argument. Like, okay, A couldn't possibly have been wrong. Because with the A, there's a kind of answer you can double check. So, okay, A is good. Let's look at B, the direction and magnitude. So yeah, here I did the left wire, right wire, enough to figure out, so your magnetic force will be pulling the things outward. So there's an outward force for each point in the wire, and I'm saying, did I not? Yeah, so I guess the part that I kind of miss is I should have written out what the this B effective was, and I definitely didn't write it out in the answer. So if you're just looking at the answer, like this is kind of leaving holes. This is where if I'm looking at student response like this, that will be what I'm wondering. What value of B are you using? And then as I look at the attached work, if I say something like this, then I'll say, okay, you know what you're doing. You just forgot to plug this into here. So now when you look at the past solutions, so yeah, there's the factor of 2 for using the average magnetic field. So yeah, I know squared. All right. So there's that. And here's the one here. And yeah, helical path, I think I got it right. On the far side, it's coming out of the screen. And did the path got erased? Oh, I used to have path drawn. What happened? Did it remain here at least? No, I think a path must have gotten erased before I... yeah, that's annoying. So just so that people remember what that looked like, I drew the path like this. Where it... Oh, I think it's taking like an erase action. That must be why. But anyways, so check for things like that before you submit your work. And so yeah, I got the path right. So helical path located from top of the solenoid. Oh yeah, and the rest, there's the drift speed. That's the component of velocity parallel to the magnetic field. The radius circle, you use that. Yeah. So I think I got that part right. So yeah, that's the one demonstration of the free-form timed assessment. So with the free-form timed assessment, I won't bother with the ChatGPT. I'll just do it myself correctly. And there is a bit of a chance that I'm taking here because I've done one question of the free-form timed assessment before, and I don't want to do the exact same one twice. So let me start and I'll get started. And just a reminder, 20 minutes, it's a really short amount of time. So I'll try to explain some things, but even for me, I have to make sure that I don't waste too much time. I will try to explain most of the things I do. hopefully correctly. Let me start. Is it gonna be the same question? No, it's slightly different. Good, good, good. Yeah, yeah. So I'll do this question. Yeah, it's a long question. I might not have enough time. So let's see. Many experiments involving magnetic field. Yeah, uniform solenoid or Helmholtz coils. I think I'm doing both. Give your answer. Yeah, consider an infinite solenoid carrying current. This made the circular laws using Ampere's law show that. Oh, yeah. Alright. Yeah, so let me do it this way. So I'm gonna have this picture on the right so that I can draw some figures that's gonna be helpful in explaining. And after sketching some of those, then I will start typing up my answer. Number one recommendation, don't leave answers blank or don't simply say see attached to the work. That's basically the same as blank. Make sure that you have stuff written in there that can be matched up with your attached work. So, given this current arrangement, or arrangement of currents, first thing I need to do is to figure out the direction of magnetic field. So, on the left-hand side, I have a magnetic field going into the screen. So, and on the right, I have magnetic field coming out. So, I think my thumb should be pointing downward. So, that means within the solenoid volume, I should have magnetic field going this way. Now, you might know that it's uniform, and I think if you use it, I won't count it against you. And you might also know that outside magnetic field is zero. I prefer to prove it, and you have seen me do that in lecture. But if you're assuming it, I won't count it against you. But I need to have a rough sense of in what direction is the magnetic field so that I can choose the Amperian loop in a way that exploits the symmetries in the setup. And that loop looks like this, going in this direction in the dotted red line. Basically, in all the segments of the loops I choose, I have one of two features. Either my loop direction, dl, is parallel to the magnetic field. That's a good one to have, because when I do b dot dl, it becomes simple. Or, in my loop direction, the dl is perpendicular to the magnetic field, which is another good feature to have, because then my b dot dl is 0. So with this choice of Amperian loop, this is what I can say. I can say, state the Ampere's law. The closed line integral of b dot dl is equal to, and I'll write it down in this form first, 4 pi Coulomb constant divided by c squared times I enclosed. And this combination of constants, it can be written in a different way that's actually more common. You could write this as mu naught, permeability of free space, but I'll go with this for now. So, and there's a whole symmetry argument you should make. There's a translational symmetry, which allows you to argue that along this segment, basically that b dot dl is constant. And there's other geometric symmetry. I guess both translational and reflection symmetry that allows you to argue that your magnetic field is pointed this way, so that you could argue that b dot dl along these segments is 0. And the b dot dl along the outside, again, I prefer to prove it. And the way to prove it is you pull that segment out to infinity, where you can argue that b must be approaching 0 there, so b dot dl is 0. And then as you bring it in, nothing changes, so even immediately outside the solenoid is 0. But I'll just say outside b dot dl is 0. Again, prefer to prove it, but if you don't prove it, that's fine. Your textbook kind of does the same thing. So starting with this, all these simplifications allows you to simplify left-hand side down this far. B times the line integral of dl of the basically just the left segment. And, oh, I haven't specified the height of the segment. let's call that arbitrary height h. You say that is equal to 4 pi, the constant you are using, times the current enclosed, and that's what you need to figure out. You are given the current density small n, so it's basically the current in a single wire times however many wires you have. So it's going to be I naught times NH. The left-hand side will simplify B times H. That H is basically this line integral by itself. That's equal to that right-hand side. So H's will cancel, which is what you're hoping for. This arbitrary parameter that I introduced is in the final expression. And this proves that B is equal to 4 pi k over c squared times I naught times n. Exactly the expression that I was trying to show. So let me just sketch it out briefly. So from the right-hand rule, within the solenoid, the magnetic field points downward. And outside the solenoid, P is equal to 0. To exploit the symmetry in the setup for application of Ampere's law, we choose the Amperian loop of a rectangular shape with a vertical size of a height h to the left of the right edge of a solenoid and to the right of the same edge. C attached figure. This would be the use of C attached, because this word description, it might be hard to understand. Figures a lot clearer. We start with the statement of the Ampere's law, which simplifies down to B times H is equal to 4 pi k over c squared times I naught n naught times n times h, and the arbitrary height h of the Amperian loop cancelling out, we get the expression we were trying to drive. Alright, how much time? Okay, 9 minutes. That's so estimate the strength of, yeah, so I think it's a matter of just plugging in the numbers. So let's just do it. We have the formula already. Let's see. Can I? Yeah, I got the formula written here. So let me just do it this way. If I copy and paste it here, that'll make it a little bit easier for the formula typing in process. 4 times pi times Coulomb constant divided by speed of light squared times current 1 ampere times the loop density. So radius I don't care, length I do care. So it should be 800 windings divided by 1 meter. This should give me an answer in Tesla. Oh, that 1 meter is grouped wrong. That should give me an answer in Tesla. Yeah, so I get 0.0101 Tesla. B101 using the formula above. C attach the screen. From Wolfram Alpha. Wolfram Alpha, using Wolfram Alpha is a lot as basically an online calculator. So, in fact, if you do use Wolfram Alpha, I think I do prefer that you attach your work. So that, I know that it comes from Wolfram Alpha and not, I don't know, ChatGPT. One is a calculator, the other one is more sophisticated tool that can provide you with the help that you are not supposed to have. All right, how much time? 10 minutes? 9 minutes, okay. Although solenoid provides the most, yeah, it's not downsize, it's completely surrounds, yeah, make access, yeah. So Helmholtz coil might be good enough, might be better in terms of access. So arrangement, yeah. Using Biot-Savart's law, show that the magnetic field due to a single loop of coil is, all right. Yeah, that's challenging. If you can't do this during the time limit, totally understandable. So you start with the statement of the Biot-Savart law, which says, I like the infinitesimal version. The infinitesimal magnetic field contribution is equal to the mu naught, or that's a 4 pi k over c squared coefficient times amount of current, that's what's generating the field, dl cross r hat, that gives you the direction, divided by r squared, because it's an inverse square law. So you need to have a picture in mind. So if we have a loop that looks like this, so one of the arguments that will help you with the calculation is, so consider two kind of representative current segments. One here at the top, I guess that's coming out of the screen. At the bottom here, that's going into the screen. And your direction of R head is this way, R head is that way, and this would be the direction of DL, DL. So you do DL cross R head, or DL coming at the top, coming out of the screen, cross R head. Yeah. Then your magnetic field goes in this direction as DL cross R head. Let me do it from my perspective so that I can make sure it looks right. So DL cross R head. Wait, what? No, DL cross R head. Yeah. I'm doing it both from both perspectives. As long as I'm using my right hand, I'm not mirroring. It should be fine. So for the contribution from this segment should then be so DL cross R head. Yeah. So going this way. Yeah. So going somewhere like this. Let me do it from my perspective to be sure. So into the screen. Yeah. So what this should be demonstrating is that there is a pairwise cancellation of these perpendicular components, so that the net magnetic field will only going this way. So you can just take the component along the z-axis for the net field calculation. So that justifies me doing just this. dBg is equal to 4 pi ke over c squared times, now dl cross r hat. Dl and r hat, are they always perpendicular? I think they might be. So it's just IDL. And the only thing I need to worry about, yeah, because I think that and that is perpendicular, and like this segment and R, that would be perpendicular, yeah. So good. And then I have R squared, which I'll need to express in terms of the, so that's the radius, and that's G. So radius, let me do capital R. So the lowercase r squared, the distance squared, should be the radius squared plus g squared. Now, stopping here doesn't give you the right answer. You have to make sure to take only the g component. So with each one of these, you imagine this theta, then the g component of that, so this theta will be that theta. So you are taking the sine theta of that. So let me write it as a sine theta for now. And the triangle that will help me figure out that sine theta later is this triangle theta, RG. So sine theta should end up being the r divided by the square root of the hypotenuse, r squared plus g squared. So with all that, dB is 4 pi ke over c squared. I'm almost there. I'll double check the time to make sure that I won't run out of time. Raised to the power of 3/2. So let's see, how much time do I have? 4 minutes, it might be enough. So here, so the final step that I just need to integrate this around the ring. And that integral is actually super easy because nothing here depends on the parameter as you go around the ring. The fact that DL and R head was perpendicular didn't change. The distance even doesn't change. So basically this integral around the ring, it ends up being just integral around the DL to pi R. That's it. So you get the answer of 4 pi k over c squared times I times R over all those constant factors times the integral, which will be just 2 pi r. And because the question already told you the expression you are getting to, you can compare that and see that you are right. Did I miss it? Oh, I made a mistake. In the statement of Biot-Savart's law, there's a divided by 4 pi here. So that cancels that out. So I had a mistake in the statement of the law. So without that mistake, you have 2 pi ke over c squared I r squared g squared. Yeah. So we work out the direction of the infinitesimal magnetic field contributions, according to Biot-Savart's law. The components perpendicular to the g-axis cancel out, so we can just take the component parallel to the g-axis and integrate them around the ring to get the result. We do need to work out the geometry, see attached, to get an expression for the sine theta for taking the component parallel to the g-axis, and the integral ends up being simple because none of the parameters depend on the parameter that varies as we go around the loop. See attached for details. I think if I saw this, I would feel comfortable enough, like reading this description and then seeing this, I can see, oh yeah, they kind of match up. So, all right, I got what, 2 minutes? 1 minute. In the Helmholtz, yeah, I don't have enough time to do this. Nearly, yeah. So, I know I can do this in Sage Math, but I have 1 minute left and I can't do it in Sage Math in less than a minute. I'll attach finish the work. So I'll leave it there and I'll start building up. Yeah, it's gonna submit automatically. I'll let it do that. And let me just start building the stuff in Sage Math. Do I need this? I don't really need it, but let me just minimize it. So for Sage Math portion, I'll use Sage Cell. So what I need to do is I need to build an expression for B total. That's gonna be the magnetic field due to the two coils. So I need to build in some variables. Yeah, it'll do that. And I'm pretty sure. Let me time myself doing this. Now I'm doing it this way now because now there's no time limit. But like if I were doing this in a hurry, I might not actually use SageMath because it's actually more time consuming. So let's current R T. I think that might be enough. I also need a D from the descriptions there. So B total is going to be B1 plus B2. Let me build B1 and B2. B1 is going to be basically this expression, 2 pi times Ke divided by C squared times I squared divided by G squared plus R squared raised to this power. But we need to shift it. So this is the expression if the loop was right at the center, G equals 0. We need to shift it a little bit to the left to G equals minus D over 2. So what the procedure will be is wherever I see G, I replace that with a G plus D over 2. And you can kind of test it out. Plug in G equals 0. Then like for this location, it looks like it's for a location that's a plus D over 2 from the loop. That looks right. So that's a B1, magnetic field due to the left loop. B2, magnetic field due to the right loop, will be this thing except with the minus sign here. So that's B total. Let's just print B total to make sure that I have it. Yeah, I got something. So for the question, what they were asking, show that the first and the second derivative with respect to G is 0. Like show that this is 0 and then that is 0. So I can just take the derivative. Derivative if B with respect to G. I think that's going to give me something. Oops. B total with respect to G. Yeah, it did something, right? I think that's right. And out of that expression, I need to substitute in G equals 0. So this is giving me a function of G, but I don't want that. I want, after taking the derivative, want to substitute it G equals 0. 0. Yeah. So I'll say print result of the diff B total G subs G equals 0. And then I'll print that. And then for the second line, it's going to be the same thing, except it'll be second order. Second order. Oh, what? Oh, I need to plug in. So this is true for any separation, but the second derivative only goes to 0 if D now is equal to R. So you actually need that. What? You can see that this is, I think, equal to, oh, no, there's a slight difference, 7, 5, what are you doing to me? Yeah, I think we're fine. I have R to the 4th power here in the numerator. In the denominator, yeah, so I can tell it to assume that R is positive. So assume R is positive. Yeah, good. It wasn't doing some of the simplifications it could, because if R is complex, then this, substitution would have been. Yeah, so actually, I don't think I need to do this substitution here. I can do this out here. So after assume r greater than 0. Yeah, good. And just to make sure it's not a, I don't know, freak accident or whatever, we could do this, print result of, because now the third derivative shouldn't go to 0, because there's no reason for it to. So for third derivative, maybe it goes to 0. It might still. If it goes to 0, I'll check the fourth derivative. Fourth derivative definitely shouldn't go to 0. There's at some point where some higher order derivative doesn't go to 0. So let me try the fourth. All the odd derivatives might be going to 0 for symmetry reasons, like for the reason this was going to 0. So this is just like a double check to make sure the code isn't doing something weird. Yeah, there it is. So let me just paste this into my work. And how much time did I take for that? I took, 6 minutes. That's a long amount of time. So if I was under time limit, like if I had 3 minutes, then I know I could do this. I might not be wasting time with Sage Math. But this time I could, because I was already outside the time limit. And so I did. So, all right. I think that's good enough. So let me just paste in the work and then move on. So as I've said before, I do recommend that you organize your work. Don't do what I'm doing right now, kind of pasting in basically what is a scratch work, but do make sure you include the work, because otherwise what you do, it's a lot harder to make a sense of what you do if there isn't some attached work. I'm not saying that I can always make a sense of what you do if there's attached work, but the chance of me being able to understand goes way up when there is attached work. So anyways, let me attach this. So yeah, this is a long question. When I saw those 4 parts, I kind of knew I couldn't finish it in 20 minutes. So I finished in maybe 25 minutes, 26 minutes. It's it's long, but not unreasonably long. You definitely should be able to do parts A and B and make a good progress on part C. That I do believe is possible for a lot of people. So anyways, because these are all manually graded, it's not drawing. And after the due date for me, which will be I guess after this Friday, I should be able to see the key icon as a test student.